I got a comment saying that it was helpful for me to do the daily problem, so I'm gonna keep doing that. By the way, I do take your comments very seriously, so if you have any thoughts about any ways I can do things better, just let me know. If you prefer, let me know if you prefer me just like completely going in blind, or if you prefer me really like knowing the solution and maybe doing like a more of like a detailed walkthrough. You definitely get more of like your bang for the buck there, but maybe you want like the more like raw way that I think second to second. I don't know. I'll just keep on going back and forth between those two because I think that there's benefits educationally to both of them. Or if you maybe it's good for me to go in blind because if you're way better than me at this, you can let me know what I'm doing wrong. All right, 2134 minimum swaps to group all ones together. Two. A swap is defined as taking two distinct positions in an array and swapping the values in them. A circular array is defined as an array where we consider the first element and the last element to be adjacent. Given a binary circular array, nums, return the minimum number of swaps required to group all ones present in the array together at any location. So for example, this one right here, you could swap the second and third position, and then you have all three ones in the same place. Well, in like one big group. And the only, and yeah, so it would just be one because you need to do one. But yeah. And then the other consideration is like if you had a one here and two ones here, that would also count. So what do we do? What do we do? Okay. So let's see. Let's open up the editor. But I feel like this is a matter of simplifying it. Because the first thing that I'm recognizing is that I'm pretty sure that a way you can simplify this circular array is just by doubling the array. Because for the sake of this problem, all that really matters is the positioning of everything. It doesn't really matter if there's two of something. Because in theory, the array is infinite anyway. So it doesn't really matter if we double it, right? So if we double it, then we could have all of the permutations, including the circle or the wraparound, but without having to do any actual wraparound technique. So let's start by saying nums equals nums plus nums. Okay, so this should handle the wraparound. We're going to turn the circular array into regular array. Okay. So now, it's important that we just understand the question. Because in our understanding, usually we'll get an idea of what to do. So my first thought would be that the solution would be to just fill in the zeros around the biggest group of ones. So you had to find, because if we move like this one right here, then we got to move its buddy. So they're a package deal. So we'd rather just move this one over to where the party is. So it's just about finding the biggest group and then bringing all of the other ones over to that. Thankfully, this isn't a matter of actually moving them. It's just a matter of figuring out how many it would be. So it's even easier. But yeah, so it's just about, like, if we have 1, 1, 1, 0, 0, 0, 0, 1, 0. Because remember, we can move them to any destination. So it doesn't matter how far away they are. It's not like it's a matter of, like, okay, we had to move this 1, 2, 3, 4. We can just move this once to be over here. So it's just a matter of moving it to where the party is. Easy enough? I think. So how do we define where the party is? And sometimes it helps to think about it like the best case scenarios and the worst case scenarios. I think you oftentimes learn something from that. Worst case scenario, the solution would just be the number of ones minus one. Because if they're all like, if it's a huge array and they're all like evenly spaced between a huge number of zeros, then we just have to take each one and put them next to each other one by one. So worst case scenario, it's count ones minus one. Okay. Now what's the best case scenario? The best case scenario is they're all grouped together already. Okay, and let's see. Let's work from the best case from there to see if we see a pattern. So the best case is this. Oh, okay, here we go, here we go. So the way we'd recognize that the best possible case is for all of them to be grouped together, being that when you go through the array, you find them all in the same range, and that range is the length of the number of ones. Here we go. This is a sliding window approach. A sliding window approach is like iterating through an array, but you iterate through it with a range rather than one at a time. This way, we can check all of the we can find the biggest group of ones. So for example, if we had 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0. So we'd count the ones and we know that we need a range of 4 ones, because the best case scenario is all the ones are together. And if they're not together, then we need to find the most ones that are in that range, because that's where the party is. That's where the most ones are, and then you just move the other ones next to it or between it. That's fine too. So this is why you need that range also, is because, like, you know, you might also find it like 1, 1, 0, 1, and when you go over this range, you realize, okay, wait, there's 3 ones right here. There's no other range where there's 3 ones. So let's move this one to here. So really, you're just counting so the solution is going to be the number of zeros in the biggest range of ones, where the group is a range sized after the total number of ones. Okay, this is making sense. Now we just have to write it, but I think that makes sense. So yeah, you iterate through, you count the number of ones, You hold on to that. Then you iterate through with a sliding window of that size of ones. And then once you find the biggest, and you basically just try to find the biggest group of ones, and then that biggest group of ones, you take the minimum value of zeros. Easy enough. So it's a sliding window approach, and we're keeping track. It's sort of a king of the hill thing to find the minimum number of zeros in the biggest group of ones. And for that matter, since it's binary, really we just need to find the minimum number of zeros. Because if the range is 4 ones and there's 1 0, there has to be 3 ones. So we don't really need to keep track of them. And the number of zeros is the number of zeros is the minimum swap. Okay, let's do this. So we've got the circular array handled, and with the solution in mind, that's not going to be a problem, because it's never going through a range bigger than, okay, so it's important. We're never going through, the reason why we can do this is because even though we're doubling the array, we're never going through the array with a bigger sliding window than the initial array, meaning that the array will never behave differently than it would circularly. Because the only way, yeah, if it's an array of entirely ones, then still we're going to iterate through it the length of that entire array, and then we double that entire array. So we're fine. We're fine. Okay, so get num1s. Okay, so the number of ones is the sum. Let's try to do this in one line. We could do we could use a sum function, and that sum function we could then take an array that would get the number of possible the number of ones going through the array nums. We would just add 1 for every single one that pops up. I think that's it. We'll see if an error pops up. Nums equals nums plus nums. So that handles the circular array. Okay, now we're keeping track of the minimum number of zeros that we find in a range of length num1. So my first thought is that we could just count, take out a splice. So like take nums like I to I plus num1s, and then count the zeros. But that'd be a lot of counting, because we can skip a step. Because 3 of the numbers, when we slide the window 1 index over, 3 of the numbers are the same. Sorry, my apologies. No, yeah, 3 of the numbers are the same. We just had to keep track of what's coming in and what's coming out. So we could keep a track of, is it 0 or zeros? Use zeros. Okay, not zeros. Makes sense. The zeros count, and that basically, we subtract a 0 if a 0 leaves as we slide the window, and we add 1 if a 0 enters as we add 1. Okay. So if that's the case, then we need to worry about the first possible permutation and then where it goes from there. Because we're going to need to work backwards, sort of, because we're going to need to worry about the 0 that was leaving, which is probably going to mean we're going to need to use I minus 1, that index, which means we're going to have to start at 1, which means we're going to have to consider the first index. So let's start zeros count with the first range. Okay, so we have our sliding window, and we're starting it at the 0th index, and we're saying, okay, count the number of zeros there if num equals 0. So this gives us the first count. Well, we're also, the zeros count is going to be like the local minima, and we need the global minima, meaning that we need to keep track of the total, the greatest possible minimum, or the lowest possible minimum. So we'll have the lowest 0 count, and that's going to equal the current zeros count for now. And then basically, as we check every possible window, we'll see if this gets beaten out by a future version of this. For I in range, and then we can start at 1 because we have already done 0. 2, and then let's see. Would we want to go the whole length of nums? I think we can just go, maybe we should just make this into a different array. Yeah. Circular nums equals nums plus nums. I want to have the original array on hand. So let's see. So if we have an array, 0, 1, 1, 0, okay, and the circular array is like 0, 1, 1, 0. Actually, maybe, okay, let's see. If it's a group of 1's, so I'm just making a group of 1's so that the max range, so that the window would be the whole thing. Because I'm curious if we had to iterate through the entire doubled array, or if we can cut it off beforehand. So if we double this, okay, and we're iterating through it in groups of 4. 1, 2, 3, 4. We don't need to do any more because this is the same as this. So I think we just iterate through it length of nums. Length of nums minus 1. No, length of nums because it's not it's exclusive for the upper bound. Okay. For I in range. Okay, so we have this count. And remember earlier we said that we only need to keep track of the 0 that's exiting and the 0 that's entering. So we can say if circular nums I minus 1. Yes, because that would get the one that was just we had just done before. Because this is 0 through, let's say nums 1 is 3. It's 0 through 3. And then now we're starting at 1. So it's 1 through 4. So we're saying, okay, if circular nums, if that equals a 0, then circular nums, no, then zeros count minus 0. And then now we consider the one that's coming in. And we don't need to keep track of if it's a 1 because it's binary. If it's a 0, if it's not a 0, it's a 1. So we only need to keep track of one stat. Because we know at any time if we have 5 zeros and the range is 8, then we have 3 1s. Okay, so if circular nums now how do we get the one that's coming in? It would be I plus nums 1 and then num 1s, and then do we subtract 1? Well, let's see. We want the one that's coming in. Okay, well, let's see. If I is 0 and nums 1 is 3, then it would be a range of 3, which means we want 0, 1, 2. So 0 plus 3 would be 3. So we want I plus nums 1 minus 1. If that equals a 0, then we add 1. Now we just keep track of the minimum one using lowest 0 count. And then we can do this simple like one-line trick. You know, next time you need to find the greatest thing when you're iterating, you can just use like min or max, and then just use min or max between either the value that you're on or its possible competitor. I like to call that king of the hill. I don't know. Because it makes sense, because there's like a king until it's knocked off by another one. And then we just say return lowest 0 count. Right? Let's see if that works. Okay, so something's off. Oh, I never actually subtracted. I said minus equals 0. Kabam! Awesome, that works. Let's see if we can make it better. Okay, pretty dang good. I think there's one way we can make it better. I always think that there's certain conditions you can eliminate right away. So we know that we can just get rid of the edge cases, the extremes, where we don't even need to consider anything. So for example, if nums1 is the entire, if num1's, if every item in the array is a 1, we don't need to do any swaps. And if every item in the array is a 0, we also don't need to do any swaps because there's no 1's to group. So we can say if num1's equals I don't know, maybe this is too considerate. I'm saying if num1's equals 0, and you notice I put that in before I did this one, and that's because this condition would get checked before this one. So if it is a 0, I want to limit the trouble of having to iterate through, well, of having to get the length of the array versus comparing it to a constant number. Return 0. Awesome. Let's see if that ups the runtime. Yes, it does. Awesome. All right, well, that was fun. Hope that was helpful. Let me know if there's any way I can be better. But that was a really good problem. I really enjoyed that. Yeah. Let me know if there's any way I can be better. Let me know if there's any problem you want me to do. And thanks for watching. I'll see you later.